Hello everyone, welcome to ME49. In this lecture we'll be covering composting and biogas generation from feedstocks such as food and farm waste. The topics we'll be going over in this video include food and farm waste in the United States, anaerobic digestion systems and the biological processes that drive them, and an example conversion from waste to methane. Food waste in the United States is enormous. Between 30 and 40% of all food produced here is wasted. In the production phase, food can be lost due to damage from pests such as insects and rodents or even disease. Occasionally, issues during production can cause food to be wasted as well. Restaurants and food retailers often overorder, and malfunctioning equipment such as cold storage can also lead to waste. Consumers by far create the most food waste, from overbuying foods at the grocery store, throwing out leftovers, or preferring to eat restaurant food over the groceries they have already purchased. In 2010, this waste added up to nearly 133 billion pounds of food, costing the economy $161 billion. On average, individuals waste $370 a year on food, which adds up quickly for households. This cost impacts food security and drives up the price of food for everyone. Additionally, food rotting in landfills releases large quantities of methane directly into the atmosphere, which is a potent greenhouse gas. Some landfills have the capability to harvest methane from rotting food, but it is largely wasted. Aside from reducing the amount of food wasted, steps can be taken to lessen the environmental and economic burden that this waste creates. Very useful products can be created from food waste, namely biogas and fertilizers. Biogas is a mixture of gases, mostly methane and carbon dioxide, that is produced from the decomposition of organic materials, such as food and farm waste. Biogas by itself can be used as a fuel, but can also be cleaned and upgraded to a higher quality fuel to be used for transport, cooking, heating, and other applications. Fertilizer is also produced as a byproduct, which can also be formulated into different varieties. In a typical anaerobic digestion system, microorganisms use biological processes to break down biodegradable material in the absence of oxygen. Inputs such as food waste, livestock manure, wastewater solids, and other organics undergo a pretreatment and then enter the digester, typically a sealed underground chamber where a mix of microorganisms consume the waste substrate and produce biogas. A vent into the sealed chamber allows the biogas to be continuously extracted, and the byproduct digestate is forced into a separate chamber where it can be collected. The end products are combustible, renewable fuel, and natural fertilizer, both of which can be further refined into other products. Anaerobic digestion and regular composting are very similar processes, with a few key differences. Regular composting is an aerobic process, meaning that the chemical reaction takes place in the presence of oxygen. Composting typically can be successful in small residential composters, which are often exposed to open air. Some of the drawbacks of regular composting are that the compost pile needs to be regularly turned, and the exposed pile may attract animals and pests. One key advantage is that the composting is cheaper and easier than anaerobic digestion, with no specialized equipment or tools required. Anaerobic digestion occurs in the absence of oxygen inside of water and bacteria-filled tanks. Once organic waste has been placed in a digester, it typically requires less labor to decompose. The key advantage of digester systems is that they're designed to collect biogas. The anaerobic digestion material flow is relatively simple. Waste feedstocks are selected and sorted and typically undergo a pretreatment before being loaded into the digesting tank. Once inside the tank, the organic waste is broken down into several steps by microorganisms, ultimately producing biogas within the main digesting tank and a byproduct digestate which is forced into the separate tank. The biogas can be used in its current state, or can also be cleaned and upgraded into processes similar to the upgrading of natural gas. The digestate can be further composted into organic fertilizer or processed into inorganic fertilizer. There are four distinct biological processes at play inside of an anaerobic digester system. The first step is hydrolysis, where hydrolytic bacteria break down complex polymers into forms that are usable for the other varieties of organisms. During this stage, enzymes are also added to boost the effectiveness of the hydrolytic bacteria. The next step is acidogenesis, where acidogenetic microorganisms produce acetate, a key ingredient in methane production. This is followed by acetogenesis, where remaining intermediates are converted to acetate and hydrogen is produced. This process is finished by methanogenesis, where methanogenic microorganisms consume the acetate and other intermediates and produce methane and carbon dioxide, the primary components of biogas. The production of biogas from a dried carbohydrate waste can be simply approximated by the Buswell-Hatfield equation. When the chemical composition of an input waste is known, the resulting quantities of methane and carbon dioxide can be calculated. This simple model assumes ideal digestion conditions and is likely to produce higher calculated quantities than real-life amounts. Constant temperature and perfect mixing, complete digestion of input waste, and no accumulation of ashes within the digester are all significant assumptions in this idealized case. Furthermore, the equation only accounts for carbon, hydrogen, and oxygen content of organic waste, which are the key components. Boyle's modified Buswell equation applies a similar simplified approach, but also includes nitrogen and sulfur content of the input waste to estimate the quantities of ammonia and hydrogen sulfide present in the produced biogas. Like the Buswell-Hatfield equation, this reaction equation is automatically balanced and assumes the same ideal conditions. Let's go through an example problem to calculate the quantity of methane produced by digestion of a food or farm waste, in this case, chicken litter. With the waste quantity and chemical composition known, we are able to calculate the resultant quantity of biogas components. We start off by solving for the subscript ratios for the input carbohydrate waste. In this example, we have chosen the hydrogen composition as the baseline ratio of 1 to compare the other elements to. By dividing all of the percentages by the percentage of hydrogen, we obtain a ratio of 7.75 to 1 to 4.68 for carbon, hydrogen, and oxygen respectively. By knowing the molar weight of each constituent element, we can calculate the molar weight of the chicken litter, and from there the number of moles of waste that it is to be digested. By plugging in our calculated ratios into the Buswell-Hatfield equation, we obtain a balanced equation tailored specifically to the chemical composition of the input organic waste. In this instance, for every 1 mole of chicken litter that is digested, 2.83 moles of methane and 4.92 moles of carbon dioxide are produced. Knowing this ratio, we can compute the number of output moles of each gas using our input. If the input quantities of sulfur and nitrogen were to be known as well, the number of output moles of ammonia and hydrogen sulfide could be computed with Boyle's modified equation.